I want you to start by picturing something in your mind's eye. Imagine a massive multi-ton chunk of raw forged steel. We're talking about like a solid cylinder of metal the size of a minivan.
Right, just absurdly heavy.
Yeah, and it's spinning at high speed. Maybe it's a component destined to become the central spindle for, one of those colossal offshore wind turbines you see out in the ocean.
Oh, wow, yeah. Those are massive.
So here is the central engineering challenge, right? How do you force a sharp cutting tool deep into that heavy, tough, rotating metal without the entire machine just violently shaking itself to pieces?
It's a truly terrifying amount of kinetic energy to control. I mean, you're essentially trying to carefully peel an apple, but the apple weighs 3 tons.
Right.
And it's made of solid industrial steel.
Yeah.
And it's rotating fast enough to crush a truck if it ever broke loose. The forces involved are just astronomical.
Well, welcome to our deep dive. Today, we're answering the multi-million-dollar engineering question that keeps that spinning steel from tearing a factory apart. We're looking into the hidden physics of the guide rail.
Yeah, it's such a cool topic.
We're pulling back the curtain on heavy machining to look at the invisible forces that make modern infrastructure possible. And it all really comes down to a fascinating battle between two very different engineering philosophies.
Exactly. It's the ultimate classic matchup in manufacturing.
Right, because on one side we have the high-speed, modern-sounding linear rails, and on the other side we have the old-school, massive hard rails, which they're also known in the industry as boxways.
Speed and precision versus just brute, uncompromising strength. And to truly understand how a lathe can carve a multi-ton ship crankshaft without tearing its own architecture apart, we first need to understand the fundamental physics of how the machine's moving parts actually travel.
We have to look at the anatomy of the slide.
Right.
Because before you can cut the metal, the tool actually has to get to the metal, And it moves along these guide rails. When we look at the two different systems, it really boils down to a deeply relatable physical concept, which is rolling versus sliding.
That's the perfect way to frame it.
So if we look at linear rails, I want you to think of them like putting a heavy box on a skateboard and rolling it across a perfectly smooth, freshly paved road.
I like that analogy.
Right. You have these wheels, or in the case of linear rails, a carriage packed with tiny recirculating steel balls. And because those balls are rolling, they only make contact with the metal track at microscopic pinpoint areas.
Yeah, that is a great way to visualize it.
Mm-hmm.
In a linear rail system, you have a modular steel track with a metal block that rides on top of it. And inside that block are those tiny spinning steel bearings.
The skateboard wheels.
Right. And this creates what physicists call rolling friction. Because the bearings only touch the track at the absolute apex of their curves, the friction coefficient is astonishingly low. I mean, there is almost no resistance.
So they're fast.
Oh, incredibly fast. They're built for extreme speed, rapid direction changes, and just incredible precision.
But then, we look at the hard rails, the boxways. And if linear rails are a box on a skateboard, hard rails are like taking a massive flat-bottomed wooden shipping crate and trying to push it across a rubber gym floor.
Exactly. It's a totally different ballgame.
You aren't rolling anymore. You have this massive flat surface area dragging directly against the ground beneath it. It's slower, it requires a tremendous amount of force just to get it moving in the first place, and it generates immense sliding friction.
And what's truly fascinating about the hard rail system is how a factory actually builds that massive sliding block. I mean, a hard rail isn't a bolted-on accessory that you just purchase from a catalog.
Like the linear rails.
Right. It is cast directly into the solid iron machine bed itself. It's one continuous monolithic piece of heavy cast iron. And this is something that usually shocks people in our era of extreme automation-skilled workers, manually scrape the iron by hand.
Hand scraping the iron. That is the detail that completely stopped me in my tracks when I was looking through the notes.
It's wild, isn't it?
It is. We're talking about machines that build the modern world, guided by computers, and yet human hands are out there with scraping tools, literally physically shaving metal off the ironways.
They absolutely have to. But here is the critical misconception.
Yeah.
You might assume they're painstakingly scraping the metal to make it perfectly microscopically flat so the two surfaces touch completely.
Right, that's what I assumed.
But it's actually the exact opposite.
Wait, they aren't trying to make it perfectly flat?
No. Because if you have two perfectly flat, highly polished pieces of heavy iron, and you stack them on top of each other and apply tons of pressure, they'll push all the air out from between them.
Oh, like a vacuum.
Exactly. They will literally suction together. The
Rough.
friction becomes so intense that the metals will actually cold weld to each other, which is a process called galling. They'll basically tear each other apart when they try to move.
So then what is the hand scraping actually doing?
So the human scrapers are creating microscopic valleys and peaks in the iron. They're texturing it. Yeah, they carefully shave away thousands of an inch of metal in specific patterns to create a network of microscopic low spots. And those low spots are absolutely vital because they give the lubricating oil a place to pool and sit.
Ah, so it holds the oil.
Right. So when that massive carriage slides over the iron, it rides on a microscopic film of oil held in those hand-scraped pockets. It's an incredibly laborious art form, but it creates a sliding surface that really nothing else can match.
Okay, so we have the skateboard versus the massive crate on a gym floor. We have rolling friction versus sliding friction with trapped oil. But if I'm playing devil's advocate here, linear rails sound fundamentally superior on paper. I mean, they're modular. You can unbolt them, slide a new one on, and your factory's back in business in a few hours. They're cheap to replace. Hard rails require an artisan to spend days hand-scraping iron, and they require constant, careful oil delivery.
It's a huge commitment.
So if hard rails are so high maintenance, slow, and expensive to build, why are they universally considered the absolute gold standard for heavy, rough machining?
That is the crucial question. And the answer comes down to two inescapable physical realities of heavy manufacturing. The first is deflection, and the second is the incredibly hostile reality of a dirty workshop.
Okay.
So let's tackle deflection first. Deflection is simply an engineering term for stiffness, or I guess rather a lack of stiffness. It's how much a material bends under extreme loads.
Kind of like standing on the middle of a wooden plank suspended between two chairs and watching it bow toward the floor.
Exactly like that. Even steel bends if you push it hard enough. Now, remember those tiny spinning steel balls in the linear rail?
The skateboard wheels.
Right, the ones that make it so incredibly fast and efficient. Well, if you take a raw steel forging that weighs 3 tons and you mount it on a machine using linear rails, you have immense static weight.
Right.
And then you drive a cutting tool into that spinning metal, adding massive downward force. All of that weight and force is transferred directly into the guide rails.
And because linear rails use balls, all of that force is concentrated on those tiny, microscopic points of contact.
Precisely. The point contact that gave them their speed suddenly becomes their fatal flaw. The pressure concentrated on those tiny docks of steel becomes so immense that the balls will literally flatten, warp, or even shatter.
Wow.
And even if they don't break, they deflect. They squish just a fraction of a millimeter.
Right.
And in machining, if your rail deflects by 1/1000th of an inch, your cutting tool moves by 1/1000th of an inch, and your multi-million-dollar part is instantly ruined.
So the skateboard wheels just completely collapse under the weight of a truck.
They do. But a hard rail acts completely differently. Because it relies on massive, flat surface contact, it disperses that heavy 3-ton load over a huge geographic area.
Oh, because it's so wide and flat.
Right. The solid iron sections spread the weight out so thoroughly that the pressure at any given square inch is actually quite low. The machine simply does not bend. When you push a heavy cutting tool deep into a forged steel blank, the hard rails stay perfectly rigid. The flat iron absolutely will not yield.
So it solves the weight issue through sheer surface area. But what about the environment? Because if we look at the reality of a heavy manufacturing floor, it isn't exactly a sterile, climate-controlled laboratory, is it?
Oh, it is practically the opposite of sterile. Heavy turning creates an incredibly violent and dirty environment. As the machine cuts, it throws off thick, abrasive cast iron dust that just floats through the air. You have razor-sharp, smoking hot metal chips flying everywhere.
Sounds like a nightmare.
Yeah, mixed with high-pressure jets of sticky chemical coolant.
And if those tiny spinning bearings in a linear rail have to operate in a cloud of cast iron dust, I mean, I can't imagine that ends well.
They absolutely despise dirt. If any of that abrasive dust gets past the seals and into the carriage of a linear rail, it mixes with the lubricating grease.
Oh, no.
Yeah, it essentially creates a grinding paste. That paste gets caught in the tiny rolling balls, scores the metal, destroys the smooth movement, and the rail essentially eats itself alive very quickly.
But the hard rail just powers through it.
It doesn't just power through, its geometry actually protects it.
How so?
Because a hard rail is a massive, flat block sliding completely flush against a flat track, there is literally no room for dirt to get underneath. The front edge of the sliding carriage essentially acts like a snowplow.
Oh, wow.
As it moves, it just physically pushes the hot chips, the dust, and the grime out of the way. It completely ignores the hostile environment. You can cut giant, filthy steel castings all day long for 20 years, and a hardened iron hard rail will just keep sliding. Its survival relies entirely on just brutal, massive simplicity.
That makes perfect sense. It's raw physical mass versus delicate complexity. But, we have to transition to something even more extreme now, because if that oil cushion or that structural rigidity fails for even a fraction of a second, we aren't just wearing the machine out faster.
We're inviting catastrophic failure.
Right. It's not just about the static weight of a part or the dirt in the air. It's about the dynamic, explosive violence of the cutting process itself. And that brings us to the concept of interrupted cutting.
Interrupted cutting is universally recognized as the place where machines truly go to die. I mean, it is the ultimate test of a machine's structural rigidity.
Let me try to visualize this because it is such a wild concept. Imagine you're driving a car down the highway at 80 miles an hour, but the road isn't smooth pavement. The road is full of deep, square potholes.
Okay, yeah.
Every time your tire drops into a hole, it violently slams back into the solid edge of the pavement. Now, translate that physics to cutting metal.
Right. Think about machining large pump bodies for the energy sector. A pump body isn't a solid, perfect cylinder of metal. It has large holes, internal cavities, and massive gaps cast right into its sides.
So your sharp cutting tool is carving its way through solid steel under thousands of pounds of pressure, and then suddenly, the steel ends.
Yeah.
The tool drops into an empty void. The pressure on the tool instantly drops to absolute zero.
Yes. And then a fraction of a second later, the spinning metal brings the other side of that gap around at hundreds of revolutions per minute, and the cutting tool violently slams back into a solid wall of steel. Crash, crash, crash.
Man.
That is interrupted cutting. It introduces severe explosive shock loads to the spindle. It sends massive chaotic shock waves tearing through the entire architecture of the lathe.
And if you're using linear rails, if you're relying on those tiny steel balls, what happens when you hit those massive potholes?
The machine bounces. The tiny steel balls simply do not have the mass or the mechanics to absorb the heavy impact of that crash.
So it just shakes?
Oh, violently. The shockwave reverberates right back up through the tool. The entire machine begins to shake violently. The cutting tool chatters against the metal, which instantly ruins the surface finish of the part, and within a few rotations it will shatter the expensive carbide cutting tip into pieces.
So how does the hard rail survive hitting a literal wall of steel at high speed? I mean, I understand that the massive iron bed is heavy, but how does flat iron dragging on flat iron actually prevent the machine from shaking itself apart?
This is where we get into the incredible physics of damping. A hard rail system acts like a giant mechanical sponge for vibration. And it all goes back to those microscopic valleys created by hand scraping.
Oh, the oil pockets.
Exactly. Because you have a massive metal-to-metal contact area, you have a huge volume of thick oil trapped between the sliding carriage and the iron bed. As the carriage moves, the motion actually pulls the oil underneath it, floating the multi-ton iron block on a microscopic fluid layer.
Like hydroplaning.
Yes. This is called hydrodynamic lubrication. It is the exact same physics as a car tire hydroplaning on a wet road, except here we're doing it on purpose.
That is so fascinating. So the metal isn't actually touching metal when it moves. It's floating on an incompressible wedge of oil.
Precisely. So when the cutting tool slams into the metal during an interrupted cut, that massive kinetic shock wave travels down through the tool and into the carriage. But before that shockwave can reach the base of the machine and cause it to shake, it hits that thick, heavy cushion of oil.
And the oil absorbs it.
Right. The fluid absorbs the impact, it dissipates the kinetic energy instantly, it eats the high-frequency vibration completely, so the machine stays dead still.
Okay, I get that the massive iron bed and the oil wedge absorb the shock, but I want to look at the point of impact for a second. The actual cutting tip is taking the initial blow before the shockwave even reaches the rails. If the machine doesn't flex, how does the cutting tool itself not just snap in half from the impact?
That is a brilliant point, and it requires engineers to use the geometry of the tool to help the machine survive. Machinists manipulate something called the lead angle of the cutting tool.
How does changing the angle save the tool?
It's all about vector forces and Newton's third law. If you hit a wall straight on, the force pushes straight back and the tool snaps. But if you grind a larger lead angle onto the cutting tool, you change the trajectory of the impact.
Okay.
You're intentionally manipulating the geometry so that the violent pushing force of the cut is directed diagonally downwards.
Oh, I see. You're forcefully pushing that kinetic energy away from the fragile tip and directing it straight down into the heavy iron bed.
Exactly. You use the physics of the angle to drive the shock wave directly down into the oil cushion in the cast iron where the machine is strongest. You're redirecting the force instead of fighting it head-on.
It's literally like a martial artist redirecting the momentum of an attacker down into the floor. That's brilliant. And to support that, engineers use other tricks, right? Like using a steady rest for long parts.
Yes, a steady rest is basically a giant mechanical claw that clamps around the middle of a long part to stop it from bowing or whipping around like a jump rope. And machinists also play with the cutting speeds to avoid a phenomenon called machine resonance.
Resonance, that's the chatter loop.
Right. Every physical object in the universe has a natural frequency where it wants to vibrate. Think of a tuning fork. If the rhythmic crashing of that interrupted cutting happens to match the natural vibrational frequency of the lathe, the vibrations will amplify each other.
That sounds bad.
It's catastrophic. It creates a feedback loop that will tear the machine apart. So by intentionally slowing down or speeding up the rotation, the machinist breaks that rhythm and stops the resonance from forming.
Okay, so we've explored the physics. We've covered the catastrophic deflection of linear rails, the hydroplaning oil wedges of hard rails, and the sheer violence of interrupted cutting. But let's ground this a bit.
Sure.
If that oil cushion fails, what are we actually destroying? Like, what kind of real-world parts demand this level of extreme, uncompromising engineering?
The scale of the components is really what justifies the immense capital investment required to build these hard rail leviathans. I mean, we're not talking about turning small aluminum bolts or automotive brackets here. We are looking at massive rotating bodies that power modern civilization.
Things like the wind turbine spindles we mentioned earlier.
Yes. Spindles that have to support the immense torque and weight of composite blades sweeping an area the size of a football field. We're talking about giant ship crankshafts. A single crankshaft that transfers the explosive power of a multi-story diesel engine directly to the massive propellers of a transoceanic cargo ship.
Wow.
Huge high-pressure oil pipes for deep-sea energy extraction, large gears, industrial hubs, train axles.
And it isn't just the final size of the part that's the problem, right? It's the condition of the raw material before they even start cutting. The initial state of the metal is incredibly punishing.
That is a major factor. These parts almost always arrive at the machine shop as rough castings or raw forgings.
Meaning they look like giant, ugly rocks of steel.
Exactly. A raw forging has been beaten into shape while red hot by massive hydraulic hammers. A rough casting has been poured as liquid iron into a sand mold. Both processes leave this tough, wildly abrasive, and uneven outer crust on the metal called scale.
So the cutting tool isn't just slicing clean metal.
No, it's punching its way through a hard, abrasive, uneven crust of baked-on scale, which introduces constant microshocks.
And the metals themselves are getting tougher, too. You have materials like duplex stainless steel.
Oh, man. Duplex stainless steel is an absolute nightmare to machine. It is structurally designed to be incredibly strong and highly resistant to saltwater corrosion. But it has a property called work hardening.
What does work hardening mean in the context of cutting?
It means that the friction of the cutting tool actually causes the metal to instantly harden right at the point of contact. If you don't push the tool in hard enough and fast enough, the tool just rubs against the steel, heating it up and making it harder and harder until the tool simply melts or breaks.
It just destroys the tool.
Yeah. To successfully cut duplex steel, you have to get under the work-hardened layer. You have to take massive, deep cuts and shear away huge amounts of metal rapidly. A light-duty machine on linear rails simply cannot generate the pushing force required to do that without stalling or deflecting.
You have to overwhelm the metal with brute force before it can harden.
Exactly.
Now, there's one part of this that seems like a massive contradiction to me. We have established that these hard rail machines are built for brute force, huge masses, and deep cuts.
Right.
But they are also uniquely suited for machining something completely different. Giant, thin-walled metal rings for energy plants. It's so counterintuitive. How does the raw, blunt mass of an iron bed protect a delicate, fragile, thin-walled part?
It is a brilliant paradox, honestly, and it brings us right back to the giant sponge. A large, thin-walled metal ring acts exactly like a giant church bell.
A bell.
Yeah. The very moment a sharp cutting tool touches the side of it, the metal wants to ring. It wants to vibrate violently.
Because it lacks the internal mass to stabilize itself.
Exactly. If you try to cut a thin-walled ring on a lighter machine, the vibration of the ring transfers down into the machine vibrates back, and the whole system starts singing and chattering.
And it ruins the part.
The surface of the part ends up looking like a washboard. It's totally ruined. But if you mount that delicate ring to a massive iron machine bed with hard rails, the sheer raw mass of the lathe acts as an unmovable anchor.
The oil wedge dampens the bell.
Precisely. The vibration tries to travel down, but it hits the cast iron and the oil cushion, and it just dies instantly. The heavy iron bed physically stops the thin ring from vibrating. It's a perfect synthesis of mass, friction, and fluid dynamics, solving a delicate problem.
So let's bring all of this together. What is the fundamental takeaway for you, the listener, from this deep dive into the hidden physics of manufacturing? It is actually a beautifully simple bifurcation in engineering logic. If your factory needs to produce thousands of small, lightweight parts with lightning-fast speed, rapid movements, and pinpoint precision, you rely on the rolling friction of linear rails.
Right, you let those tiny steel bearings do their delicate work.
But if you are tasked with wrestling huge amounts of raw metal away from massive multi-ton workpieces, if you have to shatter the abrasive scale of a raw forging, survive the explosive shock waves of interrupted cutting, or overpower a metal that fights back like duplex steel, you absolutely must abandon the skateboard.
You have to choose sliding friction. You have to rely on the monolithic mass of cast iron, the painstaking art of hand-scraped metal, and the physics of hydrodynamic oil wedges to survive the violence of heavy manufacturing.
So the next time you're standing on the coast and you look out at a massive offshore wind turbine slowly sweeping its blades against the sky, or you see a colossal cargo ship pushing millions of tons of steel and freight into a harbor, I want you to look past the finished product. I want you to picture the hidden heavy-duty lathes that dragged those components into existence.
Yeah, picture the manual laborers scraping iron until it holds the perfect pool of oil.
Picture the flat, solid iron blocks and the microscopic fluid cushions that silently absorb the explosive shock of carving the modern world.
It really is the invisible foundation of our entire industrial infrastructure.
It's the bedrock of it all. But before we wrap up today, I want to leave you with one final provocative question to ponder. It's sort of a thought experiment based on where material science is currently heading.
Okay.
We just spent this entire deep dive establishing that these hard rails rely on pure, brute, physical mass like the literal weight and sliding friction of iron to conquer incredibly tough modern materials.
Using 19th century physics to solve 21st century problems.
Exactly. But what happens tomorrow? Humanity is constantly inventing dramatically denser, incredibly resilient, heat-resistant superalloys. We need them for next-generation aerospace engines, hypersonic flight, and deep-sea exploration vessels.
They're getting harder and harder to cut.
Right. So if the raw metals we need to cut keep getting exponentially harder and tougher year after year, will we eventually reach a breaking point? Will we hit a day where even a